כל התרגיל שעשיתי לפני זה התחיל ב3 שעות לחפש טעויות. שבוע לא היה לי את 3 שעות האלה. כאילו באמת, לא היה לי אותם, יש לי מבחנים. טוב, אני כל כך מעט,
לא, זה לא...
לפחות בצלצלים. טוב, זה לא יכול לעשות. לא, אני רוצה תקציב ממנה, אני ביום של ההגשה. אלא אם כן נקבל לתרגיל את זה נגיד 50. לא, אני חושבת שזה תלוי כל אחד. לא? זה מוגדל?
אוקיי. בסדר, אם יש שאלות שהיה בהם איזה בעיה מהותית בהצגה, גם חושב את זה בבדיקה. כמובן שנסתכל עם נציג. Okay, so last class today. So we continue talking about channel coding and wrap up and say some words about the exam. Okay, so we started talking about the problem of channel coding, that is communicating over a noisy channel. And before, so in the exercise, we described the main theorem to you, and we'll just go over that again and discuss it some more. So before that, I want to talk about one of the main measures in information theory, which is mutual information. So you've seen this at Rui's class last week and probably elsewhere. How many of you have seen this mutual information anywhere in your life before? Okay. Well, in your academic life.
You mean email?
No, I mean like in some other courses.
All the time, no?
Sorry?
Probably we see it all the time.
Right.
Okay. Okay. So you've probably seen it somewhere. Anyway, so let's do the conditions required for that. So entropy we've defined, we know what that is. So I want to define a conditional entropy. You've seen that before. So let's first define. So we're interested in two variables. Okay, mutual information captures the information between two variables of interest. So before that, let's talk about conditional entropy. So let's say you have a variable x and a variable y, and you want to know to quantify the uncertainty in say the variable y, given that x has a particular value. Okay, so so we'll denote by h of y given that x has value x. So this is the entropy of y, given that the x variable has a particular value, lowercase x. Okay, so that's just the entropy of the distribution P of y given x. Sum over y. Okay? So this is a regular entropy, okay? Just of the distribution P of y given x. Okay? Okay. So and now the conditional entropy of y of the random variable y given the random variable x is just this thing, but averaged over what? X with the prior of x, or with the margin of x. Okay, so that would be just the sum over x, the probability that x will take this value, times h of y given x. Okay? So this is defined as a conditional entropy. You see, so it's not dependent on a particular value of x, it's average. So it's a function of both the random variable y and the random variable x. Okay? All right. Essentially, to calculate all these things, what do you need? You need the joint distribution. If you had the joint distribution of x and y, you would have this conditional and also this margin. Okay, so usually to calculate information theoretic measures that talk about two variables simultaneously, you need their joint distribution. Okay, so then it several things hold. For example, property. So we now have several entropy measures, right? We have conditional entropy in this guy. We have the entropy of a single variable, and we also have the joint entropy, okay, which is the entropy of the variable x and y. So it holds that the entropy of x and y is the entropy of y given x plus the entropy of x. Okay? Which all makes sense. A lot of these inequalities properties make sense. I mean, this is like the uncertainty in y given x plus the uncertainty in x. Okay? That gives you the uncertainty in x and y combined. Okay? And it's also true that this, you could write it this way. Okay? Entropy, uncertainty in x given y plus uncertainty in y. Okay? So all these nice properties hold. Okay, good. What else do we want? Okay, let's give another one. If x and y are independent, then what? Sure. Yeah, the black wasn't strong enough. X, y, conditions x equals x. So right, so age x conditioned on y is what? Age x. That's it. Okay? Because x really doesn't care about y, right? Hence, okay, this is y given x. This would just be independent of x, right? So we can strike out the x and just get this. Okay? Okay. So usually good things happen when there's independence through information theoretic measures. Okay, so now we want to define the main thing. So the mutual information. Is this good? The color?
Pretty weak.
Yeah.
Blue.
That I said blue.
No, I suggested.
Information. Is this good? Okay. Good. Which was it?
No, the other one.
Okay. But you wanted. Okay. All right. So the mutual. Oh wow. Between x and y is defined as follows. So actually, the definition will look a bit strange. Well, you've seen it last week, so it won't look that strange. The information between x and y we denote it this way. Okay, these are uppercase x and y. The information, mutual information between random variable x and random variable y. Okay, is so probably the proper definition is the Kullback-Leibler divergence between the joint distribution of x and y and the product of independent x and y. Okay, so these are two distributions. This is the true distribution of x and y, and this is the distribution where x and y are independent, but their marginals are obtained from this. Okay. All right. Okay. So from this you can already conclude a bunch of things. One, it's non-negative, right? Why? Because it's DKL. When is it 0? when they're independent, right? So it's equal to 0 if and only if x and y are independent random variables. So this thing measures what? Dependence, right? It's large. Well, intuitively at least, it's large when they're dependent, and it's 0 when they are completely independent. Okay, so mutual information is in a sense the measure of independence, if you want. I mean, in the sense that it's low when they are independent. There's a lot of algorithms that try to model independence, like independent component analysis, that use mutual information as the measure of dependence or independence. Okay. For example, if you have Gaussian variables, if x and y are jointly Gaussian, how would you describe dependence for, say, Gaussian variables? What captures the dependence?
Correlation.
Right, correlation coefficient. So it turns out that the mutual information is just a monotone function of the correlation coefficient. Okay, you'll actually prove that in the exercise. Okay. The optional exercise. Is that what you said? Okay, and there are some nice properties that we can easily derive from this. Aside from what I just said. Okay, so this doesn't look like entropies immediately, but DKL and entropy is very close, right? DKL is something log something, right? Entropy is something log itself. So if we play around with this bit, you can get things like the information between x and y is the, let's say, the entropy of y minus the entropy of y given x. Obviously, it's also the entropy of x minus the entropy of x given y. And it's also, let's see, so you remember how we related this to the joint? Age of y given x. We said age of x, y is age of y given x plus age of x, right? Always remember this because it needs the x to complete itself, right? It's y given x plus x. It's sort of like an additive Bayes rule, if you want. So, right, so let's put this, say, here. So we get, entropy of y plus entropy of x minus entropy of x and y. Okay? So all of these carry fairly intuitive interpretations. This is like the uncertainty in y a priori minus the uncertainty in y after what? After having seen x. Okay? So this is like the reduction in uncertainty in y. Okay? So right. So if x and y are, say, independent, okay, then the uncertainty before and after seeing x is what? The same, right? So it's 0. Okay? So very nice measure, very intuitive. It's very helpful if you have two variables of interest, say, a stimulus you present to an animal and some measure of its neural response to calculate this thing. And it will tell you how these variables are related, to what degree they are dependent or independent. Obviously, the difficulty is what do you need to calculate this thing? Say, let's say you have 100 possible stimuli. Let's say pictures that you show an animal, and you record the spike count, and you have up to 100 spikes. Okay, so so x has 100 values, y has 100 values. So how many values altogether? The joint x and y, that's 100 squared, right? So 10,000. So pxy, you need to estimate 10,000 numbers. Okay, so you need quite a lot of trials. Those of you who've done experiments like this, it's usually in the tens or hundreds of trials that you get. So to estimate 10,000 numbers with that is pretty demanding, or it's practically impossible if you don't have so many trials. Then there are a lot of methods for trying to estimate this using not too much data. Okay, but if you can estimate it, it's good. All right. So this is.
Word about why you decided that the definition would be the detail and these are the properties. A lot of times it shows that one of those is the definition.
You mean reverse it? I think you'll see textbooks where it's defined as say this. Not necessarily. I mean, if you have, well, you could say that entropy, you need to define differential. If it's continuous variables, you need to define differential entropy, and then, but it's not, they're all equivalent, so there's no real strong sense. Yeah.
In the sense of, why do you use the information in experiments? Do we use the information in order to assess how much the random variables are dependent on another?
Yeah. Yeah, it's. I mean, it's a tool for analyzing experimental results or neural coding, right? So let's say you have a given, the stimulus say is fixed x, okay, and now you look at responses in two different cortical areas, okay. I don't know, M1 and V1 and V2, okay, and you want to understand which area carries more information about the stimulus, okay, or subproperty of the stimulus.
Yeah, that's exactly my problem. What do you mean by the information about the stimulus? I mean,
so in the sense that this gives you a measure of how much information, say, variable y carries about variable x. If the information is complete, for example, what's the maximum? Okay, this is good. It leads to another property that will answer it. Somewhat answer your question. So the information between x and y, what's its largest value? What's its maximum value? If you look at this. Sorry? That's true, but we can be even more conservative. We see it's either right. It has to be smaller than entropy of y and entropy of x, right? Because these entropies minus something, right? So its information is less than the minimum between the entropy of x and the entropy of y, right? Okay, so it's the minimum of these two numbers. It has to be upper bounded by that. So now to answer your question, if you have, if you see that the information is close to, say, one of these upper bounds, it means that it conveys, that the variable y, say, conveys all possible information about x. Okay? So, or in other words, you can use it as a comparative tool for comparing if you have two variables, y1 and y2. You want to know which one conveys more information about x. You could calculate this, and this would tell you. Okay?
How is it different from correlation coefficient?
It's more general. So you could have, for example, a correlation coefficient that's 0 and still have information. So the information will be 0 if and only if there's independence. Otherwise, it'll capture something. So it's just a more general, or say the general measure of dependence between variables. Okay?
How can the correlation be 0 and yet the information could be non-zero?
No, you could have I don't know, cases like these are the two variables, okay, uncorrelated, and there's information, right? Yeah, correlation is a weak measure of dependence.
You could have totally random responses, kind of sometimes with regards to the stimulus, but in the sense of like how strong the firing rate is in response to different, no correlation at all. So
yeah, I mean that's one example, but
choose total random firing rates for each different stimulus.
Mm-hmm.
Like always that firing rate.
Right.
Not total.
Yeah, that's another example. Okay, so correlation is just one measure. I mean, the promise of I think information theory generally and the use of immature information for, say, neural coding is that it captures whatever sort of dependence there is in there. So after, there is another challenge. After you calculate this thing, and let's say it's high, you could ask, where is it coming from? Okay, I have a lot of information, but where is it? Okay, what sort of dependence conveys that information?
Another question also, how is it going to depend on how you choose to bin the variables? You have your discrete random variables. If you're looking at firing rates, does it depend on what the
So generally, I'd say the intuitive answer is that as you bin more, you get less information. Okay, and this follows from the data processing inequality. Okay, let's say you bin one variable, so you essentially transform your there's a function on that variable. You're losing information about that variable, right? When you're discretizing and when you're quantizing more coarsely, you're losing information. Okay, so when you calculate binned information, you usually, I mean, if you had the exact distribution, you would lose information. Okay. Okay. Good. And there's another thing we can deduce from this, which is nice. Since the mutual information is non-negative, this has to be non-negative, and then we can conclude that the entropy of y given x is, what is it with respect to the entropy of y? Small, right? So this is known as the fact that conditioning reduces entropy. Okay? Makes sense, right? You have some uncertainty about the variable y, okay? After you've seen x, so conditioned on x, you've received some information, right? You know something, so your uncertainty is probably less than it was before. Okay? Is there a question about this?
No, it looks like a minus, the bullet.
This is minus? No, it's not. It's observation point. Okay. So you can deduce a lot of these things. They make a lot of sense. You can look at them and see why they're true. But you have to be careful because some things seem to make sense, but they're actually wrong. Yep.
All these things only for the discrete case, or do all these things also work for continuous?
So the non-negativity. This is. I mean, most of them would be for the continuous case as well, because this is non-negative always. Okay.
Differential entropy can be negative.
Right. But so this conditioning reduced entropy does stay true for because I didn't use the non-negativity of the entropy, just of the information. See?
Okay, but if I have, for example, a negative h of y, wouldn't the...
No, the mutual information is still non-negative because it's a DKL. Okay. So this I can write here greater than 0. Okay. So the inequality still holds. You're right that the numbers themselves could be, these two numbers could be negative, but the order is preserved. Okay. Okay. Good. Okay. So I think that's what we wanted to say for now about mutual information. There is
How could the entropy be negative?
differential entropy. You'll see in the exercise. So for continuous variables, this I don't have it here. So for continuous variables, this px log px, okay, which is the entropy. Right? Well, you can imagine it. You now have densities, okay, and it's no longer non-negative, the entropy. Okay, and that's the beauty of mutual information, that it stays non-negative. Okay, and that's why it's in a sense it's a more basic measure. Okay, so we'll have an exercise on this. Yep.
Can you please write the equation of DKS?
Oh yeah, sure. You should know it by now. No, it's fine. So it's. I remember that there's a song. It's like P log P over Q. Okay, so it's PPQ or whatever. So, or in that, what's in here gets to be up here. Okay, that's what you need to remember. Good. What else? Oh yeah, there's the data processing inequality, which you've seen in the exercise. Shall I repeat that? Data processing inequality. You've seen it. Okay. Okay. So that's it on information. Now let's go back to our channel coding problem. Yep.
What was the data processing inequality we saw in the exercise?
All right. I'll give it to you.
No, maybe we did, just the name.
Okay. So data processing inequality says something very intuitive. It says that if you process a variable, if you perform some information processing on a variable, you lose information. Okay? So if you apply some function to a variable, you lose information about it. Okay? Sorry? Okay, let me just repeat that. Okay? That we're on the same page. Data processing inequality. Yeah. Okay. You don't. Yeah. You don't gain more information. Okay. So assume x, y, and z satisfy the following. So what is this? P x y z equals p of x times p of y given x times P of Z given Y. So pictorially we would say that it looks like this. There's X. X leads to Y, and Y leads to Z. Okay. So in this case, Y is X and Y are X and Z are what? Conditionally independent given Y. Okay. You see this? Okay. This. Yeah. Okay. So let's say you have 3 random variables. Okay. So and you know someone tells you, okay, that the joint distribution P of X and Y and Z satisfy this thing. Okay. Not every 3 random variables satisfy this. Okay. Right. Okay.
What's the general form?
Okay. Good question. Generally, they would satisfy. You could always write P of X, Y, Z equals P of X times P of Y given X times P of Z given X and Y. Right? This is always true. Okay? Now, we want to assume the setting where this is true. Okay?
Z don't care about X.
Right. So Z given Y doesn't care about X. Okay? Which means basically that Z and X are independent given Y. Okay?
So you could just write the last two terms are equal between these formulas.
These two.
Yeah.
Yes, that's right. So, so we assume basically that P of Z given X and Y is equal to P of Z given Y. In other words, X and Z are independent given Y. Okay? So what's the simplest example of this thing happening is that when Y, you have a variable X, Y is some function of X, okay? And Z is some function, possibly a noisy function even, but only of Y, okay? Right? Then you will have this thing, that where Z given X and Y really only cares about Y, okay? So whenever you have like a data, that's why it's called the data processing inequality. So this is like a data processing chain, right? You have X, Y is some processing of X, and Z is some processing only of Y, okay?
But in some way Z is dependent on X.
Yeah, but if you didn't know Y,
So we couldn't
they are correlated, or there is information between them, right? Okay? So it's like if you know, given my parents' genes, okay, my genes are a noisy function of theirs, right? And I'm obviously correlated to my grandparents as well. But if I know my parents, I don't need to, genetically speaking, my grandparents don't convey any information, right? Right.
So we saw that on the exercise where we had one variable that is a noise of another variable and another
Function of
that was the noise of Y.
Right.
Y was the function.
Yeah, so this is it's a noisy function. I mean,
No, well, he presented, I think.
he did it for deterministic.
Yeah, it was P of the function of Y.
Okay, so this is slightly more general. Okay, so here Z could be a noisy function of Y. Okay. Right. So the data processing inequality says that in this case the information between it's wrong X and Z. Okay, the information between these two endpoints, okay, it relates that to the information between Y and Z, okay? So which one is smaller? This one is small, right? Okay? Because you can only lose information along the chain, okay? So you keep processing information along the chain. So you don't, so since Y is closer to Z and X is some processing of Y, You'll only lose information on that chain.
As the information is lower, there are less dependent.
That's right. Yeah. Hmm.
So yeah, all right. So yeah.
Okay.
So a grandparent will give you less information than your parent?
Yes, makes sense, right? Because there is more genetic noise between in that generation, right? My parents could have been complete mutations with respect to my grandparents, right? And then in a good or bad way. And, anyway, so okay. So this obviously holds also if one of these dependencies is deterministic. Okay. So it's a useful thing to know. Okay. So I'll tell you just one reason why it's useful. So say X is a stimulus, okay, and this is say the spike train, okay. So this is some bunch of images that you present to an animal, and this is the spike train. Sorry, this is the spike train of some neuron that you measure, okay. So y. So y, let's say, is the random variable that is all the spike train. Okay? And now you want to measure. So measuring the joint statistics of the stimulus and the spike train is hard. Why? Right. The spike train has a lot of possibilities. Right. If we measure a second in millisecond precision, there are 2 to the 1,000 possible spike trains there. Okay. So what people usually do is they take, instead of the spike train, they take, say, the spike count. Okay. So this would just count how many spikes there are here. Let's say 10, 15, etc. Okay. So now you have much less possibilities for this random variable z. Okay. And you could calculate the information. So this becomes more practical to calculate the information between x and z, right? Okay. So what does this tell you? It tells you that the information between the stimulus and the spike count is less than the information between the stimulus and the. Yeah, well, you could. It's also true. I mean, there's also this thing, right? Yeah. I could have written this as well. Okay, it doesn't care what direction. This is also true.
Why present?
Sorry? Here?
Why stand for?
The spike train.
Coming from the stimulus, resulting from
Yeah. Okay.
Just formality question.
Yep.
When you conduct an experiment,
Mm-hmm.
and you wanted to calculate the joint information between x and y, you know the distribution of x because this is the unconditional variable that you use. You control the condition.
If it's a stimulus, that's right. Yeah.
But you don't know actually the probability of y in this sense.
You estimate it from data. That's right. Yeah. Okay. There are some cases where also estimating the probability of the stimulus is hard, like when you work with natural stimuli, natural images. You know, you let an animal, I don't know, fly around campus, and also people have them, stuff like that. Then the stimulus is also very complex. Yep.
Why couldn't there be cases, like intuitively something unclear, why couldn't there be cases that it defines it as something more efficient than y, something that clears some of the noise that you have in y, such that you'll be able to classify x more precisely, and then you have more information?
Because if it's noise, then by definition you can't remove it, right? If it's noise that deletes some information about x, okay, then you can't unnoise it or denoise it. You just see in this case, z only sees y, so it only sees the noisy version, okay?
But
So if let's say for example, I take a picture with a bad camera, okay? And now I try to do, and then you have some denoising algorithm, okay? And z is your denoised version, okay? And now we want to do face recognition on, say, y or z, okay? So it's clear that if I do face recognition on y, I could do whatever you do on your Z. For example, I could apply your algorithm, right? Okay, so let's say X is the face, Y is the noisy image, and Z is your denoised image, okay? So you got as input only the noisy image. So you can't do better than what I can do with the noisy image, right? Okay, whatever you can do with it. I can, for example, do what you did.
But won't you measure things that are noise while I will not?
No, because you only see the noisy thing. You don't have, this is, in this chain, okay, your Z only sees Y, okay? So whatever smart thing it can do to Y to get information about X, Y can do to itself to get information about X, right? So you can't invent more information than you had here, okay?
But you can do things we have.
You can, I mean, you can create a system in which you have.
Yeah, but then, since we're talking about information here, okay, so information sort of says, this is the best you can do, okay? This measures all the information between these variables. It doesn't tell you how that information is conveyed, how the readout will look like. It doesn't tell you anything like that. It tells you, this is, all the dependence that we can, exists between these things, mostly the good, okay? So you're right that if you apply a dumb algorithm to Y and a smart algorithm to Z, this won't hold, but we're not talking about that. Okay?
But you can use some prior knowledge about the distribution of X to get more information and like find edges in the noisy image.
Yeah, but you're right. So in this, but the information here takes P of X into account. Okay? So to calculate I, X, and Z, Px goes into that. Okay, so it captures the information subject to these marginals. Okay? But you're right, generally, obviously, to decode, you should use the prior on X. Okay.
I think that a lot of time we attribute filters to things that are because we're looking at the specific parameters of the signal.
Mm-hmm.
So we think that this is actually improving our signal because we applied some filter or something like that.
Yeah, but I think that's okay. So in an information theoretic sense, okay, you're not gaining more information. You just, for example, here, what do you gain? You move to somewhere where you can estimate these statistics reliably. Okay, so calculating the information between X and Y, while nice to think about, is impossible statistically. Okay, you can't calculate the exact information here. So you say, okay, I'll look at some other measure, and the advantage is that I am going to be able to say something statistically valid about this. Okay, this is why in the hypothesis that you test when you do science, you usually test hypothesis that you can test statistically in a significant way, right?
People also often kind of take this theorem to imply that higher cortical regions can't have more information than the primary sensory.
It is true. I mean, it is. You might think it's, well, let's say the retina. Okay, here's a semi-philosophical question. It's not philosophical, it's actually, I mean, the answer is here. Does the retina contain more or less information about the world than V1, or all the brain behind the retina?
But that's a definition about information. What is information? Like we treat information like something that is already we can understand easily.
Well, but that's not what it is, right? Information. Let's say information is it means more or less. If you see that variable, how well can you predict the other variable? Okay, this is not. I need to refrain that, but more or less, how well. It's a measure of predictability, right? When there's high information, it means one variable can be successfully predicted from the other. When there is no information, they're independent and there is no prediction, right?
The higher cortical region has access to auditory input.
Okay, but now you're cheating. Okay. No, you're saying you're asking a question about the visual world. Okay. If you say okay, so let's.
Yes, about the visual world.
So okay, so let's restructure the question. Let's say, if you take all the inputs into the brain, okay, all the sensory inputs from, you disconnect, now there's a quarantine on the brain, you cut all the things going out of the brain, and you put, this is your Y there, okay? So, and the Z is whatever happens inside the brain.
That also includes stored memory. Like Z is able to store the path of those inputs. Whereas
Okay, so let's say in this game everyone gets to see all the memory. Okay. No, okay. But the point is, okay, no. So Itamar, let's do another example. Okay. Let's do a simpler example. Okay, where you say there's a stimulus in the world. It's a pixel on a screen. Okay, or maybe one of 10 possible stimuli on the screen. Okay, and now you get to see either the retinal input or all the brain. What's better?
What's being presented to me is IID.
Well, let's say it's IID and it's a simple, it's a stimulus, and you need to figure out something about the stimulus. Okay, then the retina is better, right? Okay. Done. No, but it's a very good question. I think when people say that the retina contains all the more information than the brain, it's not a nonsensical statement. Okay, it makes sense precisely in this sense. Okay.
I think it's given kind of given IID, no kind of how you treat the
It's not necessarily IID. It's whether this variable here, in the example that you gave, it's no longer true that this chain holds, because Z has information on X via another arc. Okay? All right. Fair enough. Okay, good. So let's move on to... Oh, there's no cheating. This is math, right? So it's we can... Okay. So I want to go back to the problem of channel coding. Which I think, the point in presenting this theorem to you, this noisy channel coding theorem, is just to give you another interpretation of what information is. And I think it's important to know. Okay, so the setting is that we had is we want to send one of capital M messages. Okay? So we have messages 1 to M that we want to send to someone. Okay? But the way we can do it, we have to do this thing via some physical medium. So there's a channel, okay, whose input is objects of type X, and output is objects of type Y. Okay? So in the most common example, the inputs X would be bits, and the outputs would also be bits. But it doesn't have to be that. You could have an example where X is bits, so 2 options, and Y is 3 options, where one option is I don't know. Okay, this is called an erasure channel. But there are many other possibilities. Okay, and we assume. I didn't say it last time. We assume that the channel is what's called memoryless, in the sense that if I send a sequence of bits x1 to xn, if I send a sequence, so let's say I send a sequence of bits x1 to xn, then the output is y1 to yn, and we need a simplifying assumption, so it makes sense to assume that every yi depends on what? Only on xi, right? So this is what we mean by memoryless channel. So p of yn given xn is just the product over I of p of yi given xi. Okay? So actually, real physical channels probably don't necessarily have this property, because they do have some memory. Okay? Because noise, where does noise come from? It's a result of some physical process. So the physical process that was involved in noising or adding noise to x1 is probably still around for x2. Okay, so there would be some correlation between the noises, but this is a simplifying. Okay, so this is the game. We want to send one of the messages. Each message will get a sequence of let's say bits. I'll call them bits just to simplify. Okay, but generally they could be symbols of some other form. Okay, so I have the messages 1 to m. Each one is going to get some bit sequence. Okay, so I'll call this the encoding function, which is denoted by f of how do you want to say it? Okay, f of w. So this message I'm going to denote by a variable w. So f of w is going to be the code word for w. So it's some sequence of bits, 0, 0, 0, 1, 1, 1, 1, 0, etc. Okay? Okay? So every message gets a sequence of bits, and we're assuming for this game that the number of bits is fixed. Okay? So we don't have variable length as we did in coding. Because now we're dealing with a much harder problem, so we're not going to be greedy and try to play with the length. We'll just use the same length throughout. Okay? Is that clear? Okay. So now so the game is we take this W, this is the message that we want to send, we encode it. Okay, this is called the channel coding. So we code it for the channel. Okay. And then what happens at the other end of the channel? Yep.
The length we use always going to be the minimal length we need in order to code all of the words.
We'll use some length that we hope will work. Okay, the longer the length, the more likely it is that we'll be able to communicate without errors, right?
Or with less.
So we are not talking now about...
With less errors. Yep, sorry?
We're not talking now about how we'll choose our length. We're just saying that...
Yeah, I'm just in the definition stage, okay? So these would be n bits. Now, after this thing, so we have W, this is the word. We have f of W, this is the encoder. Now comes the channel, right? What happens after the channel? Right, we have some output, y, yn, right? N bits. And then we need the decoder, right? So the decoder will be some g of yn, okay, which will take the output of the channel and return some words, okay? Okay, and this, we return some estimate of the original word, okay, w hat. And we want w hat to be close to w, hopefully. Okay, so that's the game. And as I said before, and Roy probably iterated again, it's impossible if you just use a finite number of bits, it's impossible to communicate without errors. So we need n to go to infinity. So that's the bad news. But we say, okay, if n goes to infinity, let's drive m to infinity as well, okay? If we have to use an infinite number of bits, let's try to send an infinite number of messages, okay? That's the ambition. It's not clear that it's viable, but it is. So let me just define the rate of code. The rate of a code is, we define it as R equals log m over n. So we'll use a base of 2 here, because that's the common thing. But that's just a multiplicative constant. So what does this mean? If, for example, I had 8 messages, how could I encode them? And no noise, how many bits do I need to encode them? Log 8, right? So this measures the number of bits that you would have encoded the messages with no error, right? Okay? And this is the number of bits that you actually used, okay? So this fraction is the number of bits that you convey over the number of bits that you actually use. So this is sometimes measured in bits per symbol, people would say, okay? So it's the number of information bits that you conveyed over the number of symbols that you use, okay? All right, so in the binary example, could this be greater than 1? If you have binary input and output, then the best you can do here is 1, right? If you want to communicate without errors. Because if you have 8 messages, okay, and you need at least 3 bits to communicate them, right? Okay, so if you want to communicate without errors, then you want m to be 8, then n has to be at least 3, right? Okay.
When you calculate alpha, you have to put 2, or you suppose to put the...
So the convention is that it's 2, okay?
But if I use like 3 letters?
Even. So it would just be measured in bits per symbol. Okay, you could use, I mean, you could have thought of using log d here, where d is the size of x and y, but just the convention is that you use this. Okay.
So if you distribute it as R decreases, the channel coding is more efficient. Is less
As R-
bound to mistakes.
Well, R is a property of your code. Okay.
Yeah.
This says how much information do you convey relative to how much resources you use. Okay. So what you would want is a large R, right? Because you want to convey a lot of information using little resources.
Yeah, but
Yeah,
taking into account the fact that I'm prone to make mistakes if I use only small code, then
Right. So the question is, what is the best R you can get?
okay.
This is the question, and the answer is the theorem that and you've seen it, and we'll see it again next.
We'll have
hour.
a bound.
Yeah. Tight bound. All right.
When 6 goes to infinity,
Yes.
to
Yes.
be
Yes.
to be
If you want probability error of 0, n has to go to
I said
infinity.
about bounds. Infinity tends to be it tends to be tight. Infinity. No.
Okay. It's tight in the sense that there is a code that achieves it. That's what I mean.
So n has to be n כאילו
סליחה שנייה. הלו. כן, בדיוק ההפסקה.
אמרת
כן.
שנשמע אותו קודם?
כבה את המיקרופון.
קיביתי אני חושב. אז יש שם צינור ניקוד?
אנחנו לא שומעים אותו, זה לא יודע.
זה דברים כאלה קורים בכנסת כשמנהיגים נפגשים.
האובמה הזה.
המנהיג הזה כזה נורד. תראה מה היא לבשה היום. אם אתה מתייחס, אם אתה לא רואה את הבעיה ללא מי שאתה מסתכל באמת על ערוץ פשוט כאילו של העברת אינפורמציה. כמו שהוא אומר כאילו אז זה שעון של אלעזר או משהו כזה? זה לא שלי. השם מנסה לאבד את זה. מה, זה מנסה? ואין לו זיכרון. אמרתי שזה לא זיכרון. שנייה. למה אתה לוקח? מה אתה לוקח? לא.
השאלה אבל אם אתה עושה את הקורסים האלה בגלל שאתה רוצה...
מצלמה, המצלמה שלך זה Y.
אתה מדבר על AI.
והאינטרפטר, המחשב כאילו של...
כן, אבל אמרתי שזה לא מעניין. כן, אבל זה יודע, המוח זה לא רק...
ואז
נכון, אבל אתה יודע, אתה יכול כל מיני...
איזה בן אדם?
כן.
מאוד, אז
אני דווקא זה הדבר היחיד שכן מעניין אותי.
יכול
מה
להיות
עושה את כל זה כאילו.
שהמחשב יכול להוציא פרמטרים, כמו שהוא אמר, כאילו אתה מסתכל
כן,
נגיד
תקשיב, זה לא מעניין אותך, יש טריליון דברים, אבל בעצם נראה לי שהשימוש העיקרי של information theory זה לא בה.
זה לא האינפורמציה
זה לא ביולוגיה. יש כל כך הרבה שימושים אחרים.
שזה יצליח הרבה יותר טוב, יהיה בו יותר אינפורמציה
אתה יכול להסתדר.
מאשר ב-Y.
יכול להיות 10. אצלנו
אז
כאילו...
זהו, בגלל זה התחלנו, שיחקנו עם
כן, זה
המשתנה
גם בין 0
המקרי.
ל-1, אין מה לעשות.
בסופו של דבר מגיע איזשהו
לא, זהו, במקרה שלנו הרי המשתנה המקרי שלנו היה I של HA שונה מ-H פחות I של HB שונה מ-H, נכון? זה המשתנה המקרי. כי היה לך את היה EP.
אוקיי, נכון. אבל פשוט יש את ה... כאילו... כן.
נכון? פחות I של HB שונה מ-H. ואז כל אחד מהם הוא 0 או 1.
ולכן אמנם בין 0 ל-1.
לא, אז בין מינוס 1 ל...
לא, אבל זה כאילו היה עם... אוקיי, נניח בין...
האי שכל התחום הזה היה בתוך ערך מוחלט.
נכון, אבל נניח אני אסתכל על...
אבל המשתנה המקרה שלך הוא ה-X הזה.
סבבה, מינוס
משהו
1
בתוך
ל-1.
הערך המוחלט. זה בין מינוס 1 ל-1. אז קראתי לזה Z, ואז שיחקתי איתו כדי להפוך אותו להיות בין 0 ל-1. אז זה פשוט להוסיף לו 1, לחלק ב-2. נכון? אם את מוסיפה 1 למינוס 1, אז את מקבלת 0. אם את מוסיפה 1 ל-1, אז את מקבלת ב-2, 1 ב-2, זה הופך להיות בין 0 ל-1.
אוקיי, אז איך עשינו את זה ואיך עשיתם את זה?
אז פשוט, כאילו זה המשתנה המקרי.
שמיים לבקש שרת בקולי באמת הגעתי ביזיון. זה כתבתי זה ככה.
אני כתבתי 4. כאילו כל סעיף שאל את אותה שאלה בדיוק.
אני לא אמרתי את זה.
אז לא, לא שהספקתי שאנחנו לגמרי. זה נראה לי מוזר.
זה אח שלו.
מה זה התרגיל?
כן.
זה רודף אותי בחלומות.
לא, אותי זה לא
זה
רודף.
בכל יום אתמול.
אני לומדת כאן תקשורת. זה לא שכחתי את זה. אוקיי, אז למה זה? מה זה?
זה מה שכתוב בוויקיפדיה, אם אפשר תחום בין 0 ל-1.
אוקיי, וכי הוא לא תחום בין 0 ל-1, הוא צריך לחלק את זה סתם על ה...
אז אני עשיתי, אז הגדרתי את זה חדש, שזה טל, שזה מה שקורה לו, כאילו אני מוסיפה לו 1 ומחלקת את 2, ואז פשוט לקחתי את אז פה זה עוד לפחות בצורה כללית, ופה כאילו אמרתי, אוקיי, אני לוקחת את ה-Z שלי, שזה את ה-I פחות ה-I, מוסיפה לו 1, מכפילה בחצי. ואז הכתבתי פה את
למה זה נורא?
כי לזה הוספתי 1 ולפה ולמי הוספתי 1, אז אני בדחתנית. אז מה שקורה בפועל זה שאת פשוט מכפילה את הכל בחצי. זה כאילו כל מיני ככה. אז זה כבר, זה
גם לא נתנו פה רגע.
להתחיל ברבע.
אז אחר כך את צריכה, לא, בסוף את רוצה להגיע לרבע, הוא כאילו נתן לך, התחום שאת מקבלת פה הרבה יותר קצר מהתחום שהוא רוצה שתקבלי. אז לא משנה, קודם כל אני שמה פה חצי, ואז
וואי, אני רק חושבת מה כתוב לי בפתרון, כאילו משהו כזה.
סתם, ואז ואז רציתי פשוט להביא את זה לצורה שלו, אז חילקתי את זה לשתיים.
האמת ששתיים א' לא היה מצלם טוב.
אבל שלחתי לך את זה לשני.
אתמול לבית.
טוב, זה היה כמה שעות לפני שאת צריך להגיד.
לא, אבל אני אתגעתי. כאילו אין לי את ההגשה. לא, בסדר, יאללה, תשמעי כאן. אבל נראה לי לא ניגשת למצלם.
ממש מצחיק.
זה לא מצחיק. אין לי מה לגשת
נו,
לזה.
הם עוד לא מכירים אותך, אז הם מכירים אולי כמו השטויות שלך.
אני ברצינות גמורה. אני אף פעם אמרתי שאני לא יודעת מבחן בתואר.
כן, אבל תמיד את כאילו נלחצת ולא יודעת מה זה, ובסוף זה בין 99 ל-99.5.
פרט לקורסים שלא היה לי מושג ואני עושה. אוקיי, כן, בוא נמשיך. יש לי כאן חצי.
אוקיי, ואז פשוט
מספיק
זה לפרק את זה בצורה הכי מסודרת שיש, כדי שזה ייראה כמו שהוא רצה שזה ייראה.
סתם אני חושבת על זה.
אז נכפיל בשתיים לשני הצדדים. מה?
אין סיבה, כאילו סתם אני חושבת.
לא, כאילו הכפלתי פה בשתיים כדי לקבל פה את הרבע, ואז הגדלתי את התחום כדי לקבל את מה שהוא
זה
רוצה.
ממש יפה. יש לי בעיה שאני אעשה. ואז בשני סתם כאילו מוסיפים להוסיף בעצם h v ו-h m ומוסיפים שזה תמיד קטן מהכפיל זה וזה קטן מ-0. והגדול מ-1 ל-0 והגדול מ-1 כמובן ככה לא, אני באמת לא יכולה. אני לא שאלה חכי. לא, לא עשיתי. אני מבינה לעשות את זה ב-21. ואני צריך להגיד שלי לפני המקום, ואני קיבלתי את זה. אני אזרוק. אני גם בעד להאריך, יש מבחן ב-20. אני גם מאוד בעד להאריך, אני פשוט לא רגילה לזה. אני בעד עד ה-20. בוא נגיד את זה. אז אני זמן עשיתי כאילו אני לא
רציתי פגישה ממש קצרה אחרי. אפשר להיפגש או שתשלח לי במייל? או שאני אשאל את פורים אחר. אבל אין בעיה. Okay, let's go. Okay, so we defined the rate of a code, and we said ideally what we want is large rates, or high rates, large rates of code. Of course, and when we talk about a code, we mean that the error in W hat compared to W is ideally 0. And we said 0 is going to be only as n goes to infinity. So let's just define the error thing more properly. We want to talk about an error, the error of a code, or the error probability of a code. So an important thing to note is that, of course, the error is going to depend on which word we send here. So there could be particular, for a particular code, if we send message 1, we tend to have low error, and for message 2, we'll tend to have high error. Okay, so each word will have its own error probability. Okay, so let's say this way, given that we send word W, okay, so we take word W, which is the message number 2, let's say, we encode it, so the encoding is deterministic, it's always the same thing, then we send it over the channel, so different transmissions over the channel will result in different YNs, and therefore in different decodings, right? So there will be some probability of error. So given that we send the word there, the error is, we call it lambda W, is the probability that that G of YN, so let's denote that as a random variable, is different from W, okay? Different from lowercase w, given that we sent W, okay? So this is the probability of error, given that we sent the word W.
Shouldn't be FW?
No, FW is how we encode the W, and then we send Y, okay? So Y, capital Y, is what we put on the channel, okay? So lambda W is just the probability of error given that we sent this word. Oh, you could, yeah, it's the same, okay? It's the probability that W hat is different from lowercase w, okay? Yeah, this is just W hat, sorry. Uppercase. Okay? So every word will have its own probability of error, and now this is somewhat subjective how we want to define the error rate of the code. It could be the average over these lambda W's, and or what? maximum, right? The worst case. So we'll define the code error as the max over W lambda W. If we were Bayesians, we could have averaged this over some prior on W, but the theory is defined for this. It actually holds for averages as well, but it doesn't matter. Okay, so now we can state what we want. We want a code with large rate, R, such that as n goes to infinity, this thing goes to 0, okay? Okay, so now we just need one more component. What does it mean as n goes to have a code that has rate R as n goes to infinity? So what does it mean? It means that we're constantly increasing n, okay, because this is the regime, the infinite regime that we know things might work out. But as we increase n, we want to increase the number of messages accordingly, okay? So what does accordingly mean? If we want to use rate R, it means that m should be what? 2 to the power of nr, right? If we want to preserve this rate, okay? So we'll be interested in a sequence of codes with rate R and n goes to infinity. Okay? Again, we only hope to say something about codes that actually use an infinite number of symbols. So, but we want the rate to stay the same. Then this means the number of messages in this code will be 2 to the power of nr, but since this is potentially a what? Fractional number, then we take the ceiling value. Okay? Okay? Okay, and now the definition, the key definition is, we say a rate R is achievable. So what this intuitively means, when we say rate R is achievable, we mean that there is a code or a sequence of code as n goes to infinity that has rate R and what?
And the probability.
Right, exactly. Okay. We say rate R is achievable if there exists a sequence of codes with m equals 2 to the power of nr, and their probability of error approaches 0. Okay? So this is the goal. The goal is to understand, so this is a good thing, right? A rate R, as long as R is non-zero, it means that we're managing to both increase the number of symbols and the number of messages to infinity. Okay? It's like magic, if you want. Okay, and the answer, the beauty of Shannon's channel coding theorem is that it says that there are, for most channels, there are rates that are non-zero that are achievable. Okay? Sorry? Yeah.
When you say that something that it is achievable,
Mm-hmm.
you mean that we can get two messages out in error?
Yes, asymptotically.
Error?
Mm-hmm.
But when you write like that R is log to m,
Mm-hmm.
and if it's 1. So
If the rate is
if
R1?
the rate is 1.
Mm-hmm.
So there would be error.
Right, so rate 1 wouldn't be achievable.
Is a bad rate, and we would like R.
Well, it's wonderful, but we can't achieve it. Rate 1, okay, for bit, is the best we can do, right? We agreed on that before. That R equals 1.
If it is bit.
Yeah. Let's stay with it, okay? Then R equals 1 is great. But as you said, it's probably unachievable unless what? there is no noise. Okay? So you are right that for channels with noise, R equals 1 is not achievable. This is being too greedy. Maybe R equals 0.2 is achievable. Okay?
Okay. But how do you define that it is achievable? That the error is smaller than some epsilon?
No, that the error, so imagine this thought experiment where you have, in order to play this game of checking whether it's achievable, you have to come from home with a sequence of codes such that if I tell you I'm going to use 1 million bits now, you have a code for 1 million bits with a particular R. Okay? So if you want to show me that you have that R equal 0.2 is achievable, you have to work at home and prepare codes for every n that I come up with. You have to prepare codes for 2 to the n times 0.2 messages. Okay? And now we test your codes. Okay? We play the game where we calculate this thing here. So I try all the messages from 1 to 2 to the n times 0.2. And we play it, we test, we measure the probability of error. Okay? And we keep playing this game to infinity. Okay? And you're supposed to show me that as I increase n, the error, this thing here, goes to 0.
It's smaller.
It means that there is, let's say we want a probability error of 10 to the minus 7, you have to show to me that there is an n such that we will achieve this.
But when I increase n, R gets smaller.
No, R is fixed. That's the beauty. Okay? You want to show me for a particular R equals 0.2. You want to say R equals 0.2 is achievable.
So just a message becomes it.
Yes, this is fixed. Okay? This goes to infinity, and this also goes to infinity, but at this rate. Okay?
Okay.
Okay. So Shannon essentially provided the answer to this, and the answer is a number, and this number is the channel capacity, which you've seen in the exercise. I'll just define it again for you. Okay. The definition, the capacity of a channel. So when we say a channel is just a conditional distribution, okay? P of y given x. This describes how the channel introduces noise to the is defined as C. How we denote it? It's the maximum information between x and y. Okay. So we have x and y. You should think of as the variables that go into and out of the channel. Okay. So this, can you calculate the mutual information from this? From P of y given x? No, you need the joint distribution, right? What do you need in order to complete this two-joint distribution? P of x, right? Okay, so this is precisely what you do. You say, now I get to play with P of x, okay? I get to tweak it around, and I want to find the P of x that maximizes this, okay? Okay, is it clear how you calculate this thing? You go over all possible values of P of x, okay? So P of x is a distribution, okay? You consider all possible distributions on x, okay? For each such distribution, you calculate the mutual information of the joint distribution given by Px and Py given x, okay? And you take the maximum of it.
So you take the capacity of the best case.
The capacity is defined as the best case as the maximum information you could get these two variables to have between each other if you can play with the prior on x. Okay? I'll just write it more explicitly. So it's the maximum P of x of I'll just write the mutual information. So it's P of y given x times P of x. This is Pxy log P of y given x Px over okay, I'll write it this way. Px times, so what's Py? It's sum over x of P of y given x Px. Okay? So this is just an explicit, this is the mutual information, right? It's the DKL between Pxy. This is Pxy. Okay? This is the joint Pxy, where this is taken from, where did I get this from? P of y given x? That's the channel, right? Where's Px? It's the guy here. Okay? So this is Pxy times log Pxy, Px times, this is Py.
I need to lose the Px.
Yeah. achievable, I could write a supermode, but in most cases it would be. No, actually, it's a compact. Okay, it's a compact set, so it would be achievable. That's fine.
Set of
P-
all distributions is compact?
It's a simplex, right? It's bounded.
Yeah,
So,
okay. No problem.
and the information is also bounded. Okay, good. But you are right that it looks like a possibly daunting task to calculate this.
And how would X
What does it tell us?
diverge? Like, what would bring this price to be bigger? Like, if X is more.
So X needs to be, in a sense, aligned with the channel. So it needs to push prior probability into places that have less noise, if you want. Okay? It tries to maximize the information that you can convey between here and here. Okay? So if a particular value of y is, or for a particular value of x, y is completely noisy, you probably wouldn't put math there. Okay? That would be the intuition. Why does it help us?
Like you give me a channel and you tell me what's supposed to be the distribution of the message that I send.
No, so you don't care about this. What I claim you should care about is this C, but I haven't given the theorem yet, so I'll give you the theorem, then you should know what to care about. So this is the theorem, also known as Shannon's channel coding theorem. So this is Shannon probably 49 or something like that, which says all rates are such that R is less than C, are achievable. Okay? So this is the most important thing. It basically says that if you have a channel with capacity C, okay, any rate that is less than C, okay, this is strictly less, but never mind that, is achievable. In the sense, what does it mean? That there does exist a sequence of codes with rate R and probability going to 0. Yes?
Regardless of the actual P of X, right?
Yeah. This is P of X. Its only historical
Use the
role
design.
is calculating this number C. Okay? You shouldn't at this point think of it as anything real. Okay? And anything that has to do with the communication process. It's just an auxiliary thing used to calculate the capacity. Okay, so this is the main thing, and there's something about the equality. I'll tell you, and a rate is achievable. The rate R is achievable only if R is less than or equal to C. So, don't mind too much the second part of the theorem. It just has to do with the equality. Okay, so there are some cases where you cannot achieve equality, but you can get arbitrarily close to C, so it doesn't. Some cases you can achieve equal to C, some cases you can't, but you can't achieve more than that. That's the point. Okay, so this theorem tells you two things. You can't achieve more than capacity. Okay, there is no rate. There is no code. If you tell me that you came up with a code whose rate is greater than capacity, you're lying. But the positive point is that you can get as close to capacity if you want. Okay, so it has both a negative and a positive result. Okay, so this to answer your question, this is the practical implication here. That if you have this number C, it tells you in this particular communication problem what is the best you can do, and it's possible to do it.
And is it right for every distribution?
There is no distribution here. The only distribution here is the channel. Okay, P of y given x. This is the channel. It's the physical thing in the world that you want to communicate through. Okay, that's it. All the rest you get to determine because you get to design the code. Okay, so this tells you that for this particular channel with capacity C, you could, if you were, you could. It's possible there exists a code in the world with rate R that gets 0 error. Okay, it's not necessarily easy to find at infinity. Yeah. There is, of course, that also results on how the error decreases as you go to infinity, but for us, this is the result. Yep.
Is C type bounded?
Yeah, that's what I mean, because this says that any R less than C, okay, even C minus epsilon, okay, is achievable. It says all rates are achievable, okay? So this gives you the tightness. This gives you the impossibility of going beyond that. Okay? It's a beautiful theorem. The result, the proof is, it's fairly intuitive, but a bit detailed. So obviously, we won't do it in this 20 minutes. Yes.
So historically,
Mm-hmm.
when he worked in his telephone company,
Bell Labs.
what?
Bell Labs.
Bell?
Bell Labs. What? Well, it is a communication.
So he earned like a lot of money for them because they could send. He just reduced
You're saying
the
what?
number.
So in his time, I think he made a lot of practical impact. At his time, this result was not constructive. So I was about to say that this tells you that there exists a code like that, but at his time, when this theorem was introduced, they didn't know how to construct this code. Okay, but now
How do you code the
why not? Because the theorem, the proof is non-constructive. It uses a probabilistic argument
there exists,
to show that there exists such a code, but not how to construct it graphically. So in the, I would say, starting from around the end of the 1960s, I mean, there's various continuous progress, but Gallagher provided a family of codes called LDPC codes, low density parity check codes, that are both can achieve arbitrarily close to capacity, and their construction and decoding is also practical. Okay, so you could, this is the most useless result in a sense is there's something that's non-constructive. But I could give you something that's constructive, but where you have no polynomial time algorithm to encode or decode. Okay. So now we're at a state where we have algorithms that are both, they achieve capacity and they can be decoded efficiently. Okay, and these are these LDPC codes, and there are the turbo codes, and there are several families, polar codes as well. Several families of codes that have this property. I'll try to say maybe just a few words about that. Okay, so this is the result. This is the thing that you want to know how to calculate, this capacity. Once you have it, at least tells you how well you can do. And does tell you something more about the information in the context of this communication problem. So Roy did for you an example of the capacity for a noisy typewriter, where actually you can achieve capacity, and it's easy. Okay, so it's not easy to come up with such examples, but there you go. Okay, so I'll just tell you a few words about LDPC code. Okay, so here's the idea. Let's call them parity check codes. So the idea is this. Let's say you want to send 8 messages, okay? So 8 messages. So if there were no noise, what would you do? You do 0, 0, 0, 0, 0, 1, up to 1, 1, 1, right? Okay? But now you know there's going to be noise involved. So what do? You say, okay, for every, let's say I take the 2 bits, and I see it there is 0 and 0. So I'm going to add another bit that looks at the sum of these bits, okay? So 0 and 0, their sum is 0. And here it's 0. 1, 1, their sum is 2, which in binary is 0. Okay? So let's say I had 0 and 0, so 0 plus 1 is 1. Okay? So these are called parity check codes.
But it's the same algorithm, similar algorithm for data backup.
Yeah, of course. Data backup is a noisy channel problem. Okay? Why? What's the noise? It's in the storage, right? It's exactly this. Okay? So the idea is that you introduce bits, okay, that look at sums of bits in the word. So for example, this bit here would look at the sum of these two. Okay? Now you could introduce another bit, 2, that looks at the sum of these two, so this would be 0, 1, etc. Okay? So these bits convey information about the message that you want to store, right? So now, if I send this message out, and there's some inconsistency, let's say I sent it out here, okay, over the channel, and now some malicious noise destroyed my first bit, okay? But it didn't destroy these two. So it destroyed everything, it destroyed only the first bit, okay? So now I look at this thing, and
You know there's a
so I know there's a mistake, right? Okay?
you don't know where.
Right, okay. So now, if I had a lot of these parity bits, okay, then I could use the fact that there are probably not too many mistakes to try and decode, okay? So the idea in decoding is just to ask, okay, given that this is what I received, what's the maximum, what's the word, the code word that has maximum probability, okay? Yeah.
Does it work such that the mistake goes in the ref?
Well,
I mean, once you wrote zero.
no, because these bits are calculated from the original 2 bits, okay? They're not recalculated after the error.
So you're calculating the sum of the 2 bits, only of the original bits, and
Yes,
then
of course. This
don't
you do.
continue.
Yeah. This you do during encoding, okay? So this just, it's sort of different, if you want, angles on what you want to spend, okay? It's checksums, it's called in other contexts, okay?
So you have only 2 digits for the summation.
Yeah, no, so obviously you would need much more than this, okay? So the real codes, what happens is that you have I don't know, let's say 10,000 bits like this, information bits, plus a lot of parity check bits, okay?
10,000, right?
Well,
Same number,
some
minus
number.
one or
Yeah,
whatever.
yeah. I mean more, but you don't want too many because you want to keep the rate high, okay? But this is the idea. The idea is that you add these parity check bits, okay? And because noise, there is noise, but it can't flip all your bits. Then if you look at the parity check bits and you try to figure out what the information was, if you construct the codes appropriately and you have enough parity check bits and they look at enough bits in your sent information, you can decode with high probability without error. Okay? It's not, the math is pretty involved.
Where
Okay?
do
So
you
it's not,
enlarge your n?
so you use, the point is you use more n, you increase n.
Say not.
So now
you
instead
have
of 8, I use 16, but I would increase the number of parity bits accordingly. Okay? But the point is that you introduce these parity checks, okay? And they are sort of, they're used to infer what was said, okay? And the reason why it's practical is that in LDPC codes, which is low density parity check codes, each parity check only looks at relatively few number of bits, okay? And every bit is involved in few parity checks, okay? This is the low density stuff, and this makes it also tractable. Yep.
And there's any assumption about the maximum noise levels?
Well, so the rate,
Error rate or something like that?
the possible rate is related to the noise level, okay? The achievable rates are related to the noise level, okay? So if you have a complete noise, what would be the rate, if you have to guess?
0.
Right, okay? So in that case, you can't communicate. Okay. So this is just...
That's why ID numbers are so long.
Yeah, so generally, this is why when you store things or you transmit things, you transmit more than you just have to, okay? ID numbers are long, well, mostly because there are many people, but there are...
But there are only 7,
yeah.
8.
Well, you have checksums. You have Sifat Bikoret. Sifat Bikoret is a parity check. So same flavor. Okay. So this is the theorem. I'll ask Roy to do some more channel capacity calculations for you. They're, in a sense, maybe just a tease for you because you'll be able to calculate channel capacities for various channels, but you won't be able to come up with the codes that actually achieve those. Okay? But it's good to at least be able to do that. Okay. So in the remaining time, I want to very briefly give you an intuition, well, some property of entropy that is useful for proving both the coding result that we had, in the lossless coding result that we had, and also the channel coding. So I'll do that very briefly, just so you see at least one thing you learn. In one of these pages. So, and I think it's a nice exercise also for things that we discussed in the course. Yeah. I just want to briefly mention the asymptotic equipartition property. So remember when we talked about coding of lossless coding of n symbols, we had this counterintuitive result where encoding things jointly, x1 to xn, even though asymptotic equipartition property, it was somehow better to encode things jointly than to encode them separately. Okay, and we said there's, it's not entirely clear why that happens, so I want to give you a very simple intuition why. Okay, so the point is this: let's say x1 to xn are IID variables. Okay, so think of these as coin tosses, independent coin tosses. Okay, so if the coin is not fair, okay, then we expect these sequences. There are some sequences that are more likely and some sequences are less likely, right? If the coin really likes to fall on head, then sequences with head are more likely to be seen, right? Okay? And now, you can ask how many such sequences are there? How many such sequences that are really likely to see are there? Okay? So let's do a very simple exercise. I think it'd be nice to see. So I want to look at 1 over n log p x1 to xn. So, yep.
How to define likely to see? We want to count something that we don't know how to define.
Right. So what I want to get to is I want to define a set of sequences such that they will capture almost all the probability mass of x1 to xn. Okay. Right. So the way I'm going to do this is follows. I'm going to look at 1 over n the log probability of x1 to xn. Okay. Because there are IID, I can write this as 1 over n sum I log pxi. Okay. Now, okay. So log pxi is now a random variable. Okay. What's the probability that pxi will have some value? That I will see log p0, say? It's p0, right? Okay? So as n goes to infinity, we've done this a bunch of times, so I'll just skip over it and I'll say as n goes to infinity, this goes with high probability to what? To sum over x, px log p. Okay? We did exactly this when we talked about what was it? Hypothesis testing, the two options, and we got to K divergence also when we talked about consistency of maximum likelihood. Okay?
Go to his expectations.
No, it's not expectation. This is where with improbability. So this thing here is a random variable, right? Okay? So it could have, for different values of x, it could have different values. But as n goes to infinity, because we're essentially taking an average here of independent numbers, this is a number.
Yeah, no, I know, but it's expected.
Improbability. It's convergence in probability.
So it's expected.
It is also its expected value. You're right. Yeah. But the convergence, this is in probability. This means with probability 1, as n goes to infinity, this is what you'll see. What is this thing? Minus n. Okay? So this simple calculation tells you something pretty deep. It says that if you sample x1 to xn IID variables, and you look at this thing here, okay, 1 over n, their log probability, with high probability, it will always have this value. Okay? That's pretty cute. So what does it mean? That with high probability, if you look at what is this thing, it's p of x1 to xn. So this means that with high probability, p of x1 to xn is equal to 2 to the minus n entropy of x. Okay? This thing doesn't depend on x1 to xn. So what does this tell you about the probability of
Have you
x1 to
given
xn?
to the power of something?
Oh, this is the log. I just
Oh, okay.
log base 2.
Yeah, okay.
Okay? I just took the two extremes
Yeah,
of this.
sure.
Okay? So this says, okay, let's do this approximately. Okay? So what does it tell you about p of x1 to xn asymptotically? What's here? This is the constant, right? It doesn't depend on x1 to xn. It's just a number. So what does it tell you about x1 to xn? That they're approximately what? Asymptotically? Uniform. Okay? It's pretty interesting.
Even if the point is not fair?
Yeah. Well, they're uniform. I didn't say they're uniform in the sense that all assignments are possible. Okay, but among the assignments that are possible, okay, they all have the same, roughly the same distribution. Okay. Okay. So, okay. So let's say,
Can you repeat that, okay?
yeah.
Just about motivation.
Okay, so the motivation is to understand how x1 to xn, how this sequence is distributed as n goes to infinity. Okay, we want to understand something about
I
that.
don't know the distribution of each x. No, I know it.
You do, you can calculate it explicitly, but I want to understand in terms of orders of magnitude what's happening. Okay? So, we looked at this thing, which is a random variable, okay? Which is the probability of x1 to xn. Okay, we just normalized it a bit. And then we observe that as n goes to infinity, okay, this thing with high probability, okay, will have this value here. Minus entropy. Sorry?
How do you go from this part to this part?
Oh, this, I just used IIG here, okay?
Yes.
And then this is essentially an average over n random variables that are also IID. The value, so you can call this thing Zi, okay? Or this thing. So you have 1 over n summarized Zi,
Yes.
okay? Probability that Zi equals log P0 is exactly P0.
Okay.
And that we have this.
Okay.
Yeah.
It makes no sense because if I have a sequence, if 1 is highly probable and 0 isn't,
Mm-hmm.
0.99,
Yeah.
then the sequence of x1 to xn with x1 being 1
Mm-hmm.
is much more likely than with x1 being 0.
Right, I didn't say, okay, but this is, so this
No,
holds,
this is probability. I mean,
so this, so some, okay, this is very,
the probability that
Yep.
it will have, that the probability that the probability will be this goes to 1. So the probability
Right.
that it
The
won't
probability
be
that this holds goes to 1, right? That this left hand side equals the right hand side.
I understand the math, but
Okay.
conceptually it's very unreasonable.
Yeah, I mean, you have to stare at it for a while. I mean, I don't want to end on a confusing note, okay? So, okay, so this roughly means, let me say it this way. It roughly means that the mass is concentrated on, so it would be, so if we have a uniform distribution where this is the probability of each item, how many items do we have? It's 1 over this, which is 2 to n aj. Okay, so the intuitive result that I want you to, well, maybe just think about a little bit, is that as n goes to infinity, most of the mass resides in 2 to the power of n entropy sequences. Okay? Equiprobable sequences. Okay? So out of the possible, how many sequences are there generally? 2 to the n. So out of 2 to the n, actually, the ones that take up most of the mass are 2 to the n times entropy of x. Okay? What if x is a uniform coin? It's 1, right? And then it's odd. Why? Because if you have a fair coin, all sequences have the same probability, right? Okay?
I understand now.
Okay. But generally, is much less, okay? If you have a coin that is highly biased, okay, Hx will be close to 0, and then this will be much less than 2 to the n, right? Okay.
How can we say which one? To give them a...
Which ones are they?
Yeah.
So it's a little tricky. You could think intuitively, but it's not completely true, that if you have a coin that's 0.6, okay, then most of the mass will be on sequences where 0.6 of the results are hit, okay?
Yeah.
But it's not completely true, because in the 0.5 example, we actually have all sequences. So not only the ones where it's 0.5, 0.5.
No, but if it goes to... no, yeah. No,
Okay. So I guess I managed to confuse you a little bit, but...
Should X should be 1 because there is no dependence when it's uniformly distributed?
When X is uniformly distributed,
So
the
X-
entropy is, if it's a coin, if it's a binary variable, the entropy is 1. Okay?
Because it's log.
Log 2.
Log 2.
Log 2 of 2.
Just because it's a coin.
Yes. Okay? All right. And you can use this fact to at least get intuition on many of the information theoretic proofs, and you can see it in the notes that I asked you, just so you know this in detail. Okay, so I guess 2 minutes. Good. Right. So in terms of what we wanted you to see, I think this pretty much covers it. It's a somewhat eclectic course, I think you've noticed by now. We try to fit in, things that we think are sort of the basics of understanding how what it means to process information, what it means to infer things about a world you don't know about, which is something that you care about both as people, scientists, and neuroscientists in particular. Okay. So we try to give the mathematical formalisms that would help you think about these things. So we said, throughout the course, there's this thing of the world that is unknown, observations, and action. And basically, we played around with this model, playing with the things that are in the world that you want to estimate, the types of observation that you had,